Hi everybody, welcome to another IZDWF arcade repair video. This is the third video of a series dedicated to Cinematronics Vector Italian clone boards that I've received to be serviced. Links to the previous videos are down below in the description. This one is a Skyfire Logic PCB, which is a clone of the original Tailgunner game. The Cinematronics or Vector Beam early arcade games have a 12-bit CPU built with discrete TTL logic around 3 arithmetic units. This is the digital vector video output. This connects to the audio PCB, this one to the game inputs, and this is the power input. This label says there are missing pins. This is the solder side and there are a few bodge wires. These PCBs have no solder mask, but this one looks good considering its age. There is some corrosion starting in this point, but nothing to worry about for the moment. As it often happens, these old boards have a few ICs with broken pins. This is one of the TTL prongs. I have shown many times how to reattach a broken pin. I keep a few bad ICs to cut their pins when needed. This prom anyway needed 2 new pins, and this is the second one. Of course, I also check that it can be read correctly, and it works. Another TTL prom has a broken pin too, so it needed a new pin soldered in place of the missing one. Let's check it now. And yes, the checksum is correct. It seems I am the first one working on this particular Cinematronics clone game, so I took some notes about it. In particular, I needed the ROM physical layout, as the original game used 4 ROMs containing 2 kilobytes each, but this clone uses the older 1 kilobyte 2708 EEPROMs. All the TTL proms are instead identical to the Cinematronics ones. I use this great online identification tool when in doubt. I also have a list of the checksums of all the ROMs and proms of the boards I've repaired. Since this is the first time the ROMs of this game have been dumped, I've tried to run the dumps on the MAME emulator to check if the game can be played correctly. This game is too difficult without a joystick, but all looks fine anyway. Let's now inspect the audio PCB. Here we have the analog circuits that make all the sound effects for the game, but also the joystick analog to digital converter circuit. The solder side doesn't look too bad. This heatsink is not properly fixed, so it will need attention. A first check on the tantalum capacitors showed a shorted one that also left some burn marks on both the PCB and on the nearby connector. So I've removed the shorted one and I've substituted it with another tantalum capacitor that was unlucky enough to burn at the first power on because of an unsolved issue with the power supply. That part was shown in the first video of this series. Links as always are in the description down below. That moving heatsink could not be properly seated horizontally on the PCB because of 2 other components located under its footprint, so they added another nut under the heatsink, and of course both nuts needed some tightening. Another heatsink has the same problem. In this case, the pins of some resistors end under its footprint. However, other than the shorted tantalum capacitor, the initial inspection didn't reveal any obvious fault on this PCB. Together with a few board sets, I've received also the black and white vector monitor chassis. The CRT shows very evident fossil burns, but it was sent only for testing purposes. Can you guess on what arcade game TCRT spent most of its life? First of all, I tested all the deflection transistors with the multimeter in diode mode. And all looks good on all of them. Then I've measured the deflection yoke inductance values, mainly for documentation purposes. Together with the chassis, I've got two monitor PCBs, and this is the first one. This is the high voltage transformer, and it uses an external voltage tripler assembly. This is the primary driver transistor. This is of course the NEC PCB with two gas discharge voltage transient suppressors. And these are the two 12-bit digital to analog converter ICs. Here we have all the deflection amplifier transistors, some with heatsinks. As I've shown in the previous video, this yearly revision of vector monitors have some peculiar circuit problems, like this high voltage resistor that burns the PCB material under it. During the first physical inspection, I've also found some scratches on the insulation of some wires. That was probably some rodent checking the taste of the plastic. So I've desoldered those wires and added pieces of heat shrink insulator to cover the scratched parts. This is very important on any CRT circuit because some of the wires can carry up to 400 volts and we don't want the high voltage shorting on other circuit parts. Now it's time to check all diode and transistor junctions. Here, for example, there is some suspect junction. Voltage drop indication is too low. This one is suspect too. So I've started desoldering the suspect transistors and I can check them out of circuit. Yeah, this one is completely shorted on all pins. And here is another one, all shorted too. I started making a list of the bad parts. Some of them are BFX41 that I don't think I have in my spare parts. Even this one looks bad. And indeed, the voltage drop is too low for a working junction. Anyway, this is a very common 2N3906, so I surely have a few of them in the spare parts. Yet another suspicious one. Yeah, too low voltage drop. And it's the same in both directions, so it's bad for sure. This one must be bad too. 0.2 volts is again too low. And again, it's the same in both directions. Wow, so many failed ones. Some of the failed transistors are BC141, so I should have a few in the spare parts, as it was a common European type in the old days. And in fact, I found a couple of old stock BC141 that can replace the two failed ones. I've then ordered some BFX41 to replace the other failed transistors. So here's the board after all the failed transistors have been replaced. Now, it would be interesting to know why all those transistors failed at once, and I think the answer is given directly on the game service manual. The warning recommends to never power up the video PCB with the funnel deflection transistors disconnected, because that will result in a permanent failure. The replaced transistors are indeed all part of the deflection circuitry and will try to pass too much current if the funnel transistors are not connected, committing instant suicide. The last problems found during the initial inspection are some broken pins on the DAC ICs. Luckily, this can be repaired by scratching the rust and soldering a new pin. This other IC needs a few more pins transplanted. But it could be saved too. Finally, I've mounted the PCB into the monitor chassis. That was not exactly easy, because the frame was deformed quite a bit, since it was in the same box with the power supply and it got hit by the transformer getting loose. Everything is connected and ready for testing. They have used the same connector type for both deflection driver transistors and for the deflection yoke too, but the wire ordering looks straightforward. There is also another connector with a single wire that goes to the audio PCB for the joystick interface. Now, of course, I need to connect every board together and with the power supply. In fact, I got all the original wiring harness of this game. I just have to figure out where every connector needs to go. By the way, this is the 2-axis analog joystick. Here we have the button switches. This connector surely goes on the logic PCB. Of course, I've also received a few pictures from the original cabinet to greatly help in figuring out all the correct wirings. So, at this point, all the boards are wired. This is the digital vector video cable. And it of course goes to the monitor PCB. I've placed the high voltage probe on the CRT anode connector to check for proper operation of that part of the power supply. In the first video about this repair, I've shown and explained the problems related to the power supply. In fact, the first power on didn't go too well. You can see the red flash of a tantalum capacitor immediately catching fire. The power supply incident turned to good short circuit most of the tantalum capacitors on both the video and audio PCBs, so I ended up substituting almost all of them with regular aluminum electrolytics. After solving the power supply issue, we don't see anything on the screen and the audio board only makes a continuous sound. However, turning up the brightness potentiometer was enough to finally see some action on the CRT screen. Many vectors, however, are drawn incorrectly. Okay, I made it worse, but now I know why. Turns out that these clones, made by the Italian company Microhard, have a peculiar modification on the video PCB. It's made with just two added parts, circled in red here. They are two switches and one multi-turn 10 kΩ trimmer. I've checked all vector beam and Cinematronics schematics I could find, but there is no trace of these added parts anywhere. The modification is related to the LF13331 quad switch. As you can see on the original schematic, pin 4 of this IC goes directly to ground, as it should for proper operation. Pin 4 is the reference ground lever for the switch toggle inputs that work with 5 volts logic levels. Now, on this clone PCB, they added 2 switches and a multi-turn trimmer. The switches connect pin 4 either directly to ground or to the trimmer tap. The trimmer is connected between the plus 15 and the minus 15 volts rails. But in this way, if the reference level is enough different from 0 volts, then the switches will not toggle anymore, giving this crazy vector display. As the reference level goes 2 up or 2 down, different parts of the screen will get messed up first. However, since I can't really figure out why on earth such modification is needed or what it was intended for, I've just set the 2 switches for direct connection to ground, and at least the high score part is correct now. There are still corrupted vectors on some of the aliens as they move. I can only guess this was an attempt to correct the shakiness of this monitor, but I couldn't observe any change by turning that added trimmer until, of course, it will just suddenly mess up the vectors. If anyone has a good idea about this modification, let me know in the comments below. I decided to first solve the audio issue. The audio PCB is mostly analog electronics, so I think it might be easier to troubleshoot. Don't you think? As a first step, however, I'm going to check the interface IC that receives the sound data from the logic PCB. And indeed, checking one of the input pins, we can see it is just floating. Now, a good reason for a floating pin is that pin being broken. I didn't check the socketed ICs on this PCB during the initial inspection. However, even after repairing the missing pin, that input was still floating. To make a long story short, I found a missing connection on the cable that goes from the logic PCB to the audio PCB. So I've obtained a flat cable strip of a suitable length and I'll transplant the original connectors on the new cable. These connectors can be crimped using a small vise, by the way. I've then checked the new cable to make sure all pins are now connected. And now we don't have the continuous sound anymore, and we can hear a sound effect when the game starts. So far, so good. At this point, I really have 2 working video PCBs, so I'm quite sure the vector corruption issue is caused by a malfunction on the logic PCB, as it is unchanged if I swap another video PCB into the monitor. However, the logic PCB is in reality an entire 12 bits CPU made with quite a few TTL logic ICs, so in general, troubleshooting one of them can take quite some time. So, first of all, I'll try the few shortcuts that I can try. For example, checking the only ICs already socketed, that are the ROMs and RAMs. These clones have an additional EEPROM PCB, where they used 8 EEPROMs of the 2708 type. The flat cables connect 2 of the original ROM sockets to the additional board, and the needed additional decoder IC is under the flat cables, so not easy to test. I've decided instead to make an adapter to use 2 EEPROMs of the 2732 type, so I can entirely bypass all the added EEPROM decoding logic. By the way, the original design uses 2 different data paths, one for the odd ROM addresses and the other for the even ROM addresses. That's why we need at least 2 EEPROMs to hold all the original code. So, with some reverse engineering, I could combine the available Cinematronics Tailgunner ROM images into 2 2732 EEPROMs. And now I can test the board with this ugly contraption. Well, it is still broken, but I had to try. At this point, the last shortcut available was trying to swap the RAM ICs, and luckily, when substituting the rightmost IC, look at what happened. Yes, no more corruption. I'm still using the Tailgunner ROMs, by the way. At this point, it's time to test the game, so in order to simulate the con insertion, I connected a switch to the con mechanism wires. And yes, it works. The game seems configured for 1 credit each 2 coins. So let's try to play. Well, it's not so easy with the unclamped joystick. It seems the aim cannot be moved past this horizontal point. That's weird. But okay, it turns out that the joystick is made with 2 potentiometers connected between the plus 15 and the minus 15 supply rails, so over time the potentiometer position can shift and I must attempt to calibrate it again. This is the first attempt, but I must think about a better method. One method that works is watching the voltage output from the potentiometer and the X-deflection DAC output with 2 oscilloscope probes. That's because both potentiometers are decoded using the X-deflection digital-to-analog converter during the intervals where no vectors are drawn. So I want the voltage range output from the potentiometer to be symmetric respect to the no deflection DAC voltage. Of course, we must uncouple first the potentiometer from the joystick lever. Anyway, probably the easier method is to just move one axis of the joystick to the point where the aim is just at one extreme of the screen. Then power off everything, loosen the potentiometer nut so it doesn't turn when the lever is moved, position the lever to the end of its movement on the axis we are working on, and tighten the nut again on the potentiometer. So after a few iterations, it's working fine. Well, it's still very difficult to play with the unclamped joystick anyway. At the time of this video editing, all the Microhard games have been shipped back to the owner, so the Skyfire boardset is back on its cabinet. There is, of course, a red plastic filter over the CRT. So, it's all for this video. I hope it was an interesting repair and you learned something. If you have any question, please use the comment section below.